Hello, welcome to the presentation. This is my final project for CS421 programming language and compilers. In this project I will review a paper for comparing libraries for generic programming in Haskell. The paper is fairly old. It was published by Alexis Rodriguez in the year 2008. My name is Imangshu and I am doing this project alone. Motivation. The goal of generic programming is to express algorithms and data structure in a broadly adaptable interoperable form that allows their direct use in software construction. The paper highlights the proliferation of generic programming libraries in Haskell and the need of a systematic comparison. Then it develops a set of benchmarks that evaluates how well these libraries perform and support a typical generic programming scenario. Now, why do we want to compare? First of all, my personal motivation to review this paper stems from my experience in using generics as a Java developer myself. Although I have used generics extensively, I did not have the knowledge of internal working of those libraries. By reviewing this paper, I'm getting some internal idea of how these libraries work. Secondly, there are in general a lot of libraries available. This comparison helps us choose which is the right library for our work. And also by comparing, we might be able to produce a hierarchical structure of the libraries available to us. The third reason is that Haskell itself is powerful enough to define generic programs. Although we incur some syntactic overhead, but at least your tool chain becomes a bit simpler because we don't have to use preprocessors. Let's talk about the benchmarking criteria. So there are three main categories for the criteria. One is types, the second one is expressiveness, and the third one is usability. I'm going to talk through them one by one. First criteria is what are the data types that the generic programming function can be applied to. This is called universe size. We can have a very exotic data type such as nested data type or mutually recursive data types. So a library that cannot deal with such data types will not be considered good. The second criteria is it possible to restrict the use of a generic function to a certain set of data types? How the compiler will behave to an error, or will it throw an error if we pass an unsupported data type? This is defined as subuniverse. We will see in details how these are applied in the code. One set of criteria specifies what are the generic functions that are defined. There are a lot of subcategories defined under expressiveness in this paper, but in my presentation, I'm only going to discuss the most important ones. Rest of them can be found in the project report. Let's talk about the three most important ones. First one is a first class generic function. A function is called a first class function if another function can be passed as an argument to that function. So this is tested with the ZMapQ function. The function that applies the generic function to all of its argument constructor, as you can see here. The second point is abstraction over type constructor. This screenshot is a little blurry, but yeah, let's talk about it. So the generic map library is abstracting over f, which is a kind of star to star. This is important if, for example, you want to write a mapping over a binary tree that you have defined in other data structures. The third point talks about ad hoc definitions for data types. So can a generic function contain specific behavior for a particular data type and let the remaining data types be handled generically? In this situation, an ad hoc data type specific definitions are used instead of uniformly generic behavior. This is tested with the select salary function, which consists of cases that perform traversal of a data type, accumulating the values collected by salary ad hoc case. Usability. This defines how convenient a library is to use. These are performance, which basically compares runtimes for each functions. Portability, which means how easy it is to port a function between different Haskell compilers. Third is overhead of library use. This measures the additional programming effort required when using a generic library, including automatic generation of structure, representation, and instantiation of generic functions. Fourth is practical aspects, considering whether it is an implementation, it is maintenance status and quality of its documentation. And the last is ease of learning, which means some libraries have very complex implementation mechanism, making it difficult to learn. And as an end user or as a programmer, how easy for you it is to learn and to be able to use that particular library. All right, so far we have the criteria defined for the evaluation. Now, how do we use this information to actually test the libraries? Which is where we come to the implementation. The implementation involves creating benchmark for various generic programming scenarios. And depending on things such as, equality, serialization, traversal. These benchmark help evaluate those libraries. And the result of the evaluation we are going to see in the later slides. Um, the original paper was written in early 2008, which makes it very, very old. So the original code that was written for the project is widely unsupported. So for my project, I had faced a lot of challenges in actually running the test, which is why I wasn't able to finish all the test. But in this slide, we are going to talk about the two of them which I understood and see how the comparison go. Let's see an example for the first class generic function. We'll try to write an example for gmapq. On the left hand side, it is for the SYB or scrap your boilerplate. On the right hand side, we see EMJM. So we can see that with scrap your boilerplate, it does not have any problem implementing it. So there is no problem. So it checks on the good side. For EMZM, it is a bit more tricky, but we can still write a higher order generic function, even though they are more difficult to write than other generic functions such as equality. So to summarize the comparison, we have three different categories. One is which is basically excellent support or good support. Libraries like SABE, LIGD, Spine, they have a good support, which we haven't tested in our presentation, but these are there in the code, which I'm still trying to test successfully. There is sufficient support. For example, EMZM and Smash, they have support, but they are not as great as a SIB or LIGD or Spine. And then there are like Polylib or Uniplate, they don't have support at all. So we know which libraries are have a best support for first class generic functions. Similarly, for ad hoc definition, libraries like SIB, EMZM, Smash, Uniplate, they all have good support. And Polylib has sufficient support, and Spine and Lead has no support at all. Next is running the test. So the tests are located under slash comparison directory in the root of the project. I already have documented the steps in the GitHub repo. The link of the GitHub is in my project report and also in the at the end of this presentation. The original paper code did not have this documentation, so I think this is a good contribution to the project itself. This is a screenshot from the README file that is there in the GitHub repo. Um, next is the evaluation and the results. The benchmarking results show that libraries like Spine, EMZM, and Smash generally support more features than others, excelling in areas like universe size, first-class generic function, and performances. However, they might introduce more overhead in terms of structure, representation, and work required for the function instantiation and definition. Libraries like SAB, while they have a little bit limited features, but are easier to learn and use for a programmer. This is the final table from the comparison as described in the paper. I have not been able to run all the tests to get a table for my own, but adding this as a slide for reference. The table has three sections basically. These sections are as defined in the criteria in the earlier slide. Basically, it means that the more fuller or more black the dots are, it means the libraries are more useful. Yeah, so but the final result is that it turns out that no single library excels across all the criteria. Libraries that perform well in one aspect often struggle in others. For instance, extensible libraries like SIB3 requires more boilerplate code than non-extensible ones and support a similar universe size. On the other hand, EMZM, while providing extensible functions, complicates the definition of the higher order generic function. The choice of the best generic programming library depends on the specific use case. So, basically, in conclusion, the selection of a programming library should be based on the specific requirement and the scenarios of the application at hand. Um, yeah. Uh, Thanks for watching. A special thanks to the author of the original paper. It was a good learning experience. I will still continue to finish running all the tests and will continue to update the GitHub repo. Thanks for watching my presentation. There's a link to my GitHub repo and link to my website for any questions or concern that you want to raise. Thank you very much.